Today's lecture that I'm going to show you how to do is essentially look at a couple different simple machines. We're going to look at ramps, we're going to look at levers, and we're going to talk a little bit about gears and gear ratios. So you can just buckle up and check this out. I think you want to take notes. It may be in your best interest to kind of watch this first and kind of see where you have questions before we do more with this in class. So the bell's going to ring here in a few minutes, so don't be alarmed if the bell goes off. So that doesn't mean you have to pack up and go anywhere because, well, you're not here right now. I'm talking to myself right now. So it's just been a long day. Okay, here goes. Here's what we got. When we look at a ramp, we're talking about an inclined plane, right? A lot of times simple machines that we're looking at are referred to as an inclined plane. So we can call it one, we can call it other, we can call it both. We can call it a lot of things. So here's the setup, here's the dynamics, here's what we have going on. So we say the ramp is 1 meter off the ground, and the ramp height, or excuse me, the length of the ramp itself is 10 meters. And if I look at what we have, or look at what I'm trying to solve for, I want to start making sure I understand this ratio, that if I lift something straight up and it ends up right here, let's draw a box. If I lift it up 1 meter, or if I move it up the ramp, either way, it's going to take the same amount of work. To get here. It's just the way in which I get it there is going to be a little bit different. If I lift it straight up, it means I'm going to have to apply a larger force, yet just for a smaller distance. Yet if I use the inclined plane, right, the ramp here, I can apply just a little teeny tiny force, but the trade-off is that I have to apply that force over a much greater distance. And so what I'm trying to prove here is that the work in must equal the work out. But the way at which I get there is going to be a little different. If I just say with my simple machine here, I could say it'd be a small force times a very, very large distance, right? The total work here is going to equal the total work here. That if I were to have just lifted it, I would have had to lift a very, very heavy weight, but I wouldn't have had to lift it very far. That the total work using the simple machine is going to be equal to having just lifted it directly straight up. So let's apply this problem here. And when I look at this, maybe this light will help. That doesn't really matter. So let's say I still have I have the same ramp, 10 meter ramp length, inclined plane length, and I'm 1 meter off the ground. And I need to solve for my mechanical advantage. So my mechanical advantage, MA, is equal, let's see, my ramp length. My ramp length is 10 meters. And the height is 1 meter. So this happens to have a mechanical advantage of 10. 10, there's no unit, right? Meters cancel, 10 over 1, 10, whole value. So here's the key to this. Remember, I showed you before, if I'm going to apply a 50 Newton force over the course of 10 meters, you would be able to solve, let's see, I can actually determine the actual weight of this had I lifted it straight up. And that's really what you're going to be solving for. So I can solve, I know that on this side here that I'm working through, I'm going to solve for, well, what is its weight, right? Remember, we've determined that the F on this side, F times D, this is actually going to be the object's weight, right? F of G is weight. So here's what I know. I know that 50 newtons times 10 meters, right? This is going to equal its weight times the distance here, and I have it right here, a distance of 1 meter. So I set this up, and I'm solving for, here I have 500, 50 times 10 is 500 Newton meters. So it's 500 joules, right, which is a Newton meter, equals the weight times 1 meter, right? So 1 meter height. So I'm solving for the weight. How much would it take for me just to lift this thing straight up? I'm asking for, well, what's its weight? Well, that's what I would need to solve for. So I'm isolating F of G. So if I divide 500 divided by 1 meter, right, I'm going to divide both sides by 1 meter, I'm isolating, boom. So its weight is going to be 500 newtons is the object's weight. So if I took this 500 Newton object and lifted it 1 meter, it's going to be the same amount of work done if I apply 50 Newton force over the course of 10 meters. So there's a couple different ways I can apply this here. The mechanical advantage of 10. This is what it means. I have to do the same amount of work, but the key here is that the trade-off. Simple machines allow us to, let's just say, apply a smaller force, but the trade-off is that we apply that smaller force for a greater distance, or a proportionally greater distance. That had I lifted it directly up 1 meter is the same amount of work as me pulling it up this inclined plane. The trade-off is that I can apply a smaller force. I only have to apply that smaller force for a greater distance. And that's what I'm trying to show you here. I'm trying to quantify it. So mechanical advantage, make sure you have these in your notes. Ramp length divided by height. And mechanical advantage, in this case here that we solved for, was 10 meters. Ramp length divided by 1 is a mechanical advantage of 10. And that's the advantage I gain. So as a result of that, I only have to apply 1/10 of the force, but I have to apply it for 10 times the distance. Okay, we're going to move on. We're going to move on to levers. Levers here. We're only going to look at what your textbook calls a type 1. I've always called a first class lever. Potato, tomato. I'll let you finish that. Here it goes. Lever, first class. Here's what we got. So we need to make sure we differentiate what is happening here. So we're going to call this an input side. How we say an input side is where you, that's what we're applying to, right? We're going to be the ones here pushing down on this. We're going to push the lever down. And the output is what we want to get out of it. I want you to see here. If I push this down, it's going to be moved on this fulcrum here, like so. This is my fulcrum. This is my pivot point. Right, when I say pivot, this is what the lever is going to be moving upon, right here, boom, this point right here. And I want you to see this distance here, that this distance over here is dramatically larger than this distance over here. That my input distance is larger than my output distance. Right, simply just making this drawing right here. Input side is divided, or in the middle of it's the fulcrum. So the input and output are separated by the fulcrum. So mechanical advantage here is force output divided by force input. And this is going to be key here. We're going to start using this equation, this setup for mechanical advantage as well. So let's apply that to a problem. So with this lever here, so let's say I'm going to lift up this object. This object weighs 500 newtons. But this is, it's a heavy object. I got to lift it. So I'm going to create a lever. In this lever, I'm going to put my fulcrum near it, and we'll talk about this lever arm length here in a moment because it's going to influence my mechanical advantage. And if I want to lift this, well, that means we need to know something. Let's say I have a mechanical advantage of, let's go with 10, right? Let's say we have a mechanical advantage of 10, right? It's just been a number I've worked with. So we'll start off easy. You just need practice with this. So if this has a mechanical advantage of 10, here's the trade-off. I only have to apply 1/10 of this weight, right? My force, I only have to apply 50 newtons. But the trade-off is that I have to apply it for a distance that is 10 times larger, right? My input distance is going to be 10 times larger than my output distance. Notice, if I pull it down here, according to this, it's only going to go up that far. Here's my distance that I lift over here, and it's not drawn to scale. But you can see that here to here is much larger than here to here. So these distances are just me drawing lines connecting through the fulcrum. And so the trade-off of mechanical advantage, I can apply 1/10 the force, but the trade-off is I have to do it times 10 times the distance, right? And that's on my input side. This is all my input side. That's the side I am working on. And therefore I can lift something that's 10 times heavier, right? 10 times F of G. Right? Weight is a force. The trade-off is I only lift at 1/10 the distance, and that's why this distance here is so small. So another way I can treat this for the first class lever is I can look at the arm length. So if this is a 10-to-1 ratio, this is definitely not drawn to scale. So the way I see it, this is almost more like a 5-to-1. But let's go with 10. Let's go with 10. If I look at this, I can treat this like my lever arm input divided by my lever arm output. And I can solve this, my mechanical advantage here. If I know it's 10-to-1, that means if I'm trying to lift something over here, as long as my lever arm output is 10 times larger, so I can call this lever arm, and I'm just going to call it I for input, divided by my lever arm output. right? So this has to be 10 times longer. So if this lever arm outputs 1 meter, my input side has to be 10 meters. And therefore you would see that mechanical advantage would also be 10 meters over 1 meter, which would be a 10. So remember, the closer I put my fulcrum to the object I'm trying to lift, the greater my mechanical advantage, right? I can move my fulcrum, and that's what's so clever about these. And last but never least, let's look at gears. And I'll try to go through this as detailed as I need to. We don't have to get crazy. And I don't even draw the teeth in these. But here's what we're looking at. We need to use a terminology called a gear ratio. We're going to talk about what an input and an output gear are. So let's call this first gear right here an input gear. And let's say it has 40 teeth. Let's say the output gear has 10 teeth. I want you to think of it this way. If I rotate this one full time around, my input gear, if this goes one full rotation, this particular output gear is going to move around 4 times, right? So if I look at this, my gear ratio is going to be my output is 10, my input is 40. So it's a 1 to 4. So it's kind of like saying for every one of my input, my output gear turns 4 times. So let's say I move my input gear twice. My output gear is going to move or turn 8 times. So we can apply gear ratio. So let's try another. Let's try another different gear ratio. So my gear ratio here, my output here is 5, my input is 30, so it's a 1 to 6. So that means if my input gear, doesn't matter which way I rotate it, if I rotate it once, my output gear, it's actually going to rotate 6 times. So let's say I move this 5 times, my input gear, 5 times here. My output gear is going to rotate or move 30 times at a 1 to 6 gear ratio. So let's do this last one. We'll end on this. So this is just going to challenge it just a little bit. You just need a little practice with it. That's the primary reason why I'm making this video. You don't wake up in the morning and be like, oh yeah, I understand gear ratios and gears. It's all good. It doesn't work like that. It works like this. My input gear is 25 teeth and my output. Notice I have 2 output gears here. So my input gear is what I'm going to be turning. So let's say I turn this way. So I have a 25 to 5. So that means for every one time I rotate this input, this one here is going to rotate 5 times. And notice this 5 is only going to have, right, so it says 5 teeth. So my input gear has 25 teeth. My output gear 1 has 5 teeth. Notice my output 2 gear has 50 teeth. So this is something we have to think about. So you have to use common sense here. For me to rotate this one full time, this output gear 1, right, output 1 is what I call it, is going to rotate 5 times, right? So in this case, it's a 1 to 5. Notice, if this rotates 5 times, it only has 25 teeth. 25 is only half of this. This is only going to move one half of a full rotation. This output gear 2 is not going to rotate 1 full time. So let's try something a little different. Let's say I rotate my input gear 1. Let's say I do this one 10 times. Let's see, so 10 times. This one here is going to rotate 50 times. See how that works? And so then this one, so if I rotate this 10 times, this is going to rotate 50 times, right? So it's a 5 to 1 here, 5 teeth to every 1 here. And so if this one moves 50 times, right, this is 1/10. This one here is going to rotate a total of 5 rotations. So you get a little practice with it. This one's more of a common sense problem. Hopefully that helps.